All right, our next speaker is Chris Heistand from Stoke Space. You can totally fly a rocket with Python and Wi-Fi. You just shouldn't.
Hi, so I'm Chris Heistand. I'm the vehicle software lead at Stoke Space. Yes, you can and you shouldn't. Next. Okay, so setting the stage, last year, September 17th, was a pretty excellent day for our company. We had a stage 2 full-scale demonstrator with our actively cooled heat shield, 15 engines, or 15 thrusters around the ring. You can actually see that the active cooling created ice on the bottom. There's fire everywhere else. Did a vertical landing, or vertical takeoff, vertical land demonstration hop mission, and it worked. The basic setup was flight software in C, ground software in Python, GNC was in Simulink, our front end was LabVIEW. The onboard stuff felt pretty standard. Once you actually hand off to engine start, it was fully autonomous safing and landing, and then we'll actually talk through how we essentially had Wi-Fi as an optional flight and telemetry, flight and recovery telem setup, and why that was also exciting. But really what I wanted to focus on here is the lessons learned from using Python just as a interpreted language and kind of like how we used it on the ground software side, which it turns out for a rocket, you're interacting with the ground system at a much higher cadence, at a significantly larger throughput from a data perspective, and doing a lot of autonomy on the ground. So how did this all start? There's always this, well, I need a debug tool to interrogate my flight software. And then you're like, well, can I connect to it remotely? Sure, it has an IP connection. Okay, well, what if I want to coordinate a couple of targets? Well, I just thread this script and I can connect to a couple of these. Great. And then you want to start sequencing things, and you know, Python is a sequency, scripty language, so let's make a little API and import it and run it. Okay, and now you want to abort if things get hairy, and so you create some guardrails and make a red line logic setup, and so this should totally scale, right? The answer is no, as you can guess, but so there's like a handful of things that we learned along the way, and everybody brings up how Python is slow. Like that's, I think, everyone's favorite thing to bag on, and I don't actually quite buy it. So we pushed 247 megabits per second of telemetry getting decommutated and acted upon through our ground software. You do have to end up rewriting some of that deserialization stuff. We ended up doing that in Rust. You can do it in C just as well. So having Python orchestrate C in Rust, super common paradigm, it works very well. And it's not real time. I'm not trying to make a claim that it's real time. However, from our cycle loops and the jitter that we were measuring, we were getting like 1 to 3 milliseconds of jitter on these things. It was pretty good. But yeah, I will buy a little bit. So the GIL really, really kills you whenever you start getting into a large multi-threaded situation. In Python, it is a single global interpreter lock. And so you essentially have a single process that is in constraint with itself. And importing and running a Python sequence, if that is what you're doing as far as your sequence language, is also adhering to GIL rules. And so you can starve out your sequence and you can have it jump in the middle of your thread, go to another thread, and we'll actually get to a very exciting case there. But basically the GIL made it pretty difficult. But you can push a lot of data through Python. The next thing is you basically have to make a decision on, do you adopt the language and make an API, or do you create a DSL for what your sequence language is? So how much surface area are you exposing to users? How well can you bound that surface area, and how often do users go outside of those bounds? So think about it as a landmass on an island. You can test and bound and say, this is your API. Most of the time they stay within that. Then they start wandering. Then they get on a boat and they start finding dragons. And so for about the first 6 to 12 months, we were very, very well bounded and staying within our lane. And then we realized that we actually needed, okay, well, we have a linear state, or we have a linear set of, the sequence is set up to handle linearity very, very well, but what happens when you start needing to add state machines? What happens when people are adding conditionals? What happens whenever you need conditional red lines? And so you can make all of those things because it is just Python. It is just a language that you're using, and users will start doing that. And so this is where it was incredibly useful for exploration of the state space to know what we needed to build. But it is also very, very difficult to bound and put all those guardrails up that you actually need to put up to have a safe system. And so we'll get to the end reveal, but like essentially that. We've talked a lot the past couple of years of, oh, can you put a Lua interpreter on board, or can you put a MicroPython interpreter on board, or some other sort of interpreted language thing, and just make a little API and it'll call out to your flight software. And the question is always going to be, how well can you bound that? And how crazy are your users going to get? Is it going to be you that's creating that, or is it going to be some mechanical engineer who is just like, but I need to just do this thing, and it's Python, and I'm just going to write a for loop, and then what, right? The next thing is implicit versus explicit error handling, and this is where we're going to start looking at a couple of different languages. But when do you find errors? What language paradigms exist? And what happens when you actually hit an error, right? So like in C, you have a return code, so let's say you have an error. Something goes wrong that you're expecting, and you have to pass back a return code. Are you doing that by overloading your return? Are you doing that by creating your own sort of passing in a pointer so that you can go and send back an error that way? How are you crafting that? And really what it takes in C is a lot of careful design and somebody who is an expert to go build that thing right the first time, because that is necessary. And then you find the rest of your bugs in test, and we have C, it flies all the time. Okay, that's not a surprise to anybody. Python, on the other hand, you don't compile. You don't have any of those compile time checks. There are things that you can opt into, like MyPy and other things, but you don't actually need to be good to write Python, which is actually a problem. And so the thing with Python is that, okay, so you find something and you throw a try-catch around it. Well, try-catches are evil, and they are really just go-tos that can be ignored. And so the other thing is that, like, you are at runtime. It's super fast to iterate on. It's super fast to just run, make a tweak, run, make a tweak, run, but you don't actually know until you have run every single line of your Python code and hit every single branch, whether that is through testing or whether that is in prod, that it is actually what you wanted it to do. And that is problematic, not to mention all of the race conditions that you potentially have because of your threads. And then in comparison, in Rust, you don't actually have to be good to write good code, and well, to write code that is memory safe in Rust. But because the compiler is going to yell at you incessantly until you have something that actually works and is strongly type checked. And you are forced to understand, oh, this is a result from a function. What do you do if it's an error? What do you do if it's null? Has to be an upfront choice that the compiler is enforcing. So it's you're moving from a human needing to be good and needing to know that those things need to be checked in C, or in Python, where those things are checked just by wrapping them in a try-catch and saying, oh, but it's an error, I'll handle it somehow, to Rust, where every single function has that kind of type checking for you. And one of my favorite bugs that we hit along the way here was Python's logger eating our exceptions. So it's Python, we were importing, we were running a sequence, we had an API, set this, open this valve. Okay, cool, that's all fine. We did isolate it, so we set it up as its own thread. We were able to pass an exception to it with some C API stuff. It would kill that thread basically no matter what, and then we would be able to run our abort sequence. Cool, all of that was fine and dandy until we realized that if you sent that exception over while you were writing out in the Python logger, that it wouldn't actually stop. And so basically we were extending just exception, not base exception, but we were extending exception, and Python's logger doesn't want to die whenever it is handling exceptions and trying to output whatever you just had a problem with. And so what it does is it ignores exceptions and is able to just say, oh, if it's an exception, just write it out and just keep going and it's fine. And we were basically sending it from one thread to another to say, hey, please stop this thread completely. And logger, if it was inside that section of code, would just say no. And so we figured that out, extended base exception, that actually was able to pierce through that exception handling, and it worked as expected. But we didn't know that going in, right? And that is, again, where, like, it's just a go-to when something goes wrong that can be ignored by other pieces of code that you did not write. The next thing is package management. So in C, and then in Python, so for Python, you have this pip, right, that you can go and install whatever you want from whatever ecosystem you want. But there's like these caveats where it is whatever. It's from open source. There's interesting things that you can go and grab. That's great and fine and dandy, but they can go and move their API from under you, and that doesn't really, like, it feels very, very disjoint and disconnected. Also, don't ever mix and match VM, virtual VM, Conda, Docker, root versus user. You can install the same package with different versions in every single one of those on the same machine at the same time, right? And so, like, it's too many options. Even though you can do what you need, it's too many options. Whereas in Rust, in Cargo, it's Cargo. They finally probably have what you want now that it's 2024. Backwards compatibility actually matters. They do crater runs against every single open source thing every single time they update the version of Rust. So Rust version 1.76 to 1.77, they do a crater run of, did that language bump change anything across every single cargo or crate? And that is, like, they just actually care about that and can tell that the typeness of everything, the APIs of everything are still in working order for that next version. So anyway, I think that's just a very interesting matchup of all three. And again, it goes back to, in C, you have to know what you're doing. You also have to build it all yourself, or use a framework like CFS, or use a framework that you go and understand and are an expert in, right? And so it's yeah. Okay, and so this kind of brings me to, like, why was this good, right? Like, overall dev speed versus completeness is the trade here. It's so easy to set up and get your first prototype running and grab a package, get your first deployment out. You can literally hotfix on the edge device that you're working on by just like opening up VI or Nano and like trying another thing and running again. You can wrap your problems away with try except, and it's super responsive to figuring out your requirements, to figuring out what you need to build. But you never get there, right? So the last mile of scaling or concurrency or observability into that imported sequence, because it's not fully compiled, so you don't actually know that you had a problem way, way, way down that sequence until you actually run into that problem. And if it's within a conditional, you'll just not see it. The package consistency across the fleet bit us a couple of times. We had, like, you can just overwrite types in Python, which is a feature and a terrifying thing. And then you basically get to a point where you can, like, you build first and design later. And it doesn't have to be built well to work. And I think that that's like one of the scariest things is you can have somebody who has never written Python before, start writing Python and get to that, like, you know, 80, 90% realm. But if they're not really good at Python, they will never close that gap. Okay, so the extra credit exercise here, just because Wi-Fi is really fun and everybody talks about it. So we used Wi-Fi for best effort, flight telemetry. We also had drones out there for taking epic videos of, you know, flying a rocket. So we tested with 2 drones for interference on the pad, and everything looked good. Hop day shows up. Camera crew added a 3rd drone. 3rd drone started actually acting up with the other 2 drones. They were all fighting for the same spectrum. They brought the Wi-Fi down and kicked us off to a different access point. We ended up shutting down all the drones and flew the rocket, and that was fine because we were able to notice it through actually packet loss from measuring NTP clock drift. So just very fun. Watch your drones. They will eat 2.4 for breakfast. Okay, so the wrap up. We had a year and a half to do this and 3 people. And so our biggest thing was we needed to move quickly, understand a whole bunch of requirements that had never been written down, and basically explore the state space. And I think that for that rapid iterating prototype mentality, Python was wonderful and actually showed us all of the things that we needed to build. So it allowed a fairly graceful discovery of all of these requirements despite fighting some of the language features. And I am also convinced that if you had somebody who was just like really, really freaking good at Python, the way that we hire really, really freaking good C people, that you could do the same thing. Like, it is a language that you can, if you know the right things to opt into, and you know how to add the type checking ahead of time, and you have the right tool chains, and you have the attention to detail within that language, you can do it. The problem is that I don't think that that's necessarily who, like, that wasn't me, right? And that was not who we had on the team. And so you end up with, well, it mostly works. And so those are some of the reasons that we wholesale moved to Rust across our stack. All right, and I will leave you with just the fun video of Hopper, which does not have sound.
I don't see any sound.
So anyways, it was yeah. So so you can totally do it. You just shouldn't. All right, that's my talk.
All right, I'll do one online first. They're asking about some of the GUI front ends, about the LabVIEW choice, and maybe considering other things like Cosmos.
Okay, so honestly, one of the reasons for not doing Cosmos is I don't actually think that it would keep up. When you're pushing 100+ megabits per second of decommed data, that is a lot of data. Yeah.
Hi. So, quick question. It wasn't clear to me if you're running your automation on board or on the ground, and also if you're running on board, if you can say what target did you embed Python in?
Yeah. So we did not actually run Python on board for any of this. However, all of our engine testing, all of our ground, like prop load, all of that was automation through Python, basically. On board was C and Simulink, so the actual flight was that.
All right. Thank you very much, Chris.